Kia ora, Robert McLaughlin here. Welcome to week 11, lecture 1 for 162.04 differential equations. This week we're going to be looking at numerical methods for differential equations. As I've probably said repeatedly through the course, most differential equations can't be solved analytically to get an explicit formula for the solution. So there are some techniques you can do, as we've just been seeing in the last few weeks, but a lot of times you'll be relying on numerical methods to get approximate numerical solutions. Now, we looked at this already right back at the start of the course. We did Euler's method for a scalar differential equation. So you could start by reviewing the lecture. I think it's week 2, lecture 1 of Euler's method. And this week we will again start with Euler's method, but this time for systems of differential equations. And we'll see, as we saw earlier, for Euler's method for a single equation, it's conceptually simple, it's easy to program up, but it's not very accurate. So the critical thing for a numerical method is how large are the errors, and in particular, how rapidly do the errors decrease as the step size gets smaller. You can always reduce the errors by taking more and smaller steps. That takes more computational work and it may lead to a very long computation. So what we want is for the error to tend to zero very quickly as the step size tends to zero. So let's suppose we've got a system of first order differential equations. I'll just consider the autonomous case. Actually, for now I'll do the autonomous case and then we'll do the non-autonomous case in a second. And we've got an initial condition. Some initial time equals x0, and here x is a vector because I'm dealing with the system of n first order differential equations. And the picture that goes with this, which is particularly instructive if we're in R2, say, we know that the differential equation says at each point, for example at x0, that vector f of x0 tells you in which direction the vector x should be moving. And there's another little arrow attached to every point, and together they make up the direction field. Suppose it looks like this. Imagine a little arrow attached to every point that tells you how fast and in which direction you're moving if you pass through that point. Now we know that there's going to be a smooth curve passing through that point, always tangent to the direction field. And the idea of Euler's method is very, very simple indeed. It says start here and just take a straight line step for a certain amount of time in that direction. And I've tried to draw it there so that you see that the true solution is bending away because it's following slightly different arrows now. But in Euler's method, I just take a step in a straight direction. Straight line step. So the formula for that, to get to the next value of x, would be x1 is equal to x0 plus the time step, which I'm going to call h, times the little vector telling me in which direction I'm moving. That would take me to this point here. And then the next step, I'd be going in my new direction. So from this point, I'd be going in a slightly different direction. I'd be tracking along in a sequence of little straight line segments, and I would be drifting away from the true solution, but hopefully not too rapidly. Now let's add the time component as well, so that if I had a non-autonomous system of differential equations, dx dt equals some vector field that depends on x and on time, what would Euler's method look like now? The update to get from xn to xn plus 1, the next value of x. Still, it's very similar. I just add on the step size times the vector field evaluated at the current position and at the current time. So in terms of the picture of the direction field here, you can think of all of these arrows now being functions of time. So just imagine a little movie where the arrows all sway around as time goes on. I just, at the current instant in time, tn, evaluate the vector field at that time and take a step in that direction. And time n is going to be the initial time plus the nth step times the step size. That's Euler's method for non-autonomous systems. Now, actually doing the calculations is rather a lot of work by hand, so we're going to actually do it all in MATLAB or Octave. And the example is going to be a non-linear oscillator called the Duffing oscillator. It's a fascinating system. I won't have time today to get into all of the cool things that it does, but here are the differential equations. The acceleration is the force, which is minus x minus 5x cubed, so it's got a nonlinear force now, and it's got a damping proportional to the velocity. And if we introduce a new variable y to be the velocity, I get x prime is y prime is minus x minus 5x cubed minus 0.02y. Here's my system, nonlinear planar system that I'm going to solve numerically with Euler's method in Octave. Okay, here we are in Octave. I'm in the editor view, so I'm looking at my M files. First I set up a function M file to evaluate the vector field. So its input is the current point x, which is a vector with two components, and the current time, which actually doesn't matter, but it's just there for syntax. And then I calculate the vector field. Instead of the variables being called x and y, they're now called x1 and x2. That's just exactly the formula I wrote down earlier. And here's my Euler program. Let's just walk it through. I set up my initial time as 0. T0 equals 0. I set up my final time that I want to reach, 0.4. And then my next variable is the number of steps I want to take. And from the number of steps, I can calculate what the step size would have to be to reach T1 from T0 in n steps. It's T1 minus T0 on n steps. The advantage of doing it that way is I can then later on change the number of steps very easily, and the correct step size will be computed automatically. This vector x is the initial condition, so x is 0, y is 1. Disp here is just short for display. It's just a way of generating prettier output. Here's the core of Euler's method. It's a loop. It takes n steps, and they're numbered from 0 to n steps minus 1. First I compute the current time, t0 plus nh, display the current time and the current x, and here is the line where I actually carry out Euler's method. So I compute x plus h times the vector field on the right, and it's stored back into the same variable x again. So in this version of Euler's method, I'm not storing all of the values from the beginning to the end. I'm just replacing them in the current variable x. You could store them all if you wanted to. Okay, let's give it a go and hop over to the command window. Just type Euler. So here we go. Here's my 4 steps. Initial condition was 0, 1. In the step number, this column, the second column is the times, 0.1, 0.2, 0.3, 0.4, and here's the x and y values. So that's pretty easy. I didn't have to calculate anything. I just had to write my program. But now the immediate question is, how accurate is the answer? We're going to focus on the y value, 0.91453. Okay, I get a number, but I know it's not going to be exactly correct. The question is, what's the error? So the first thing I'm going to do is go back and change n steps to 8. Save that one. Run it again. Now it's done 8 steps. You see the time is now going up in steps of 0.05. My final y is 0.8992. Before it was 0.914. So it's quite a big change. So probably my initial value here was only accurate to 1 decimal place, 0.9. That's about all you can say. Now if I made n steps much bigger, I'd have enormous amounts of output. So what I want to do now is first off, comment out that line, because I'll now be setting n steps at the command prompt, And I'm also going to remove all my output statements. The percent there, make that into a comment. So all I'm going to be interested in is the final value. So I'm going to set n steps equal, I'll repeat 8, call the program Euler, and then print out the final x. There it is, 0.89920. N steps equals 16. 0.89154. Still changing quite a lot in the third place there. N steps equals 32. 8877. Oh goodness me. So I've hardly got up to 2 decimal places of accuracy. So that's not very good. So maybe I need massively more numbers of steps. Let's take 1,000 steps. 0.88408. Compare it to 2,000 steps. Now this is looking better. Now it only changes in the 5th decimal place. So that suggests that the first 4 decimal places are correct. But I had to take an enormously large number of steps to get that accuracy. And that was for a very simple system. So that is the drawback of Euler's method. It's just simply not very accurate. So the question now is, I'm always until I run out of computing power, I can always make the number of steps larger and the step size smaller. But the question is, how rapidly does the error go to 0 as the step size tends to 0? So let's check that out. To know what the error is, I'm going to need a very accurate value. So let's make n steps enormous. And let's use that value. Oh, it took a little while there to compute that. Let's call that exact. Store that into the variable exact. Now I can use that exact value and subtract it off to get an estimate of the error. So let's go back to n steps equals 4 again. Just 4 little steps. Run the code, and this time don't print out the solution, but print out the error, which is the exact value minus the approximate value. The prime there just does a transpose that makes it into a row vector for printing. There we go. So the error in the y value was minus 0.03. This time I'm going to go n steps equals 2 times n steps. So double n steps, store it back into that variable. Run Euler and print out the error. Now the error is 0.015. Do it again. I'm doing a little shortcut here where you press the up arrow on the keyboard and it brings back your previous command. Double it again. 0.008, 0.004, 0.002, 0.001. Okay, that's enough evidence. It looks like every time I double n steps and halve the step size, the error is halved. And that can in fact be proved using Taylor series. That is done in the accompanying PDF study guide. The result is that the error in Euler's method is proportional to the step size. And the question that we'll look at in the next lecture is, can you do better than that?